Component gases which contribute the most to air pollution are hydrocarbons, carbon monoxide, and oxides of nitrogen. Oxygen and carbon dioxide, while non-regulated, play a significant role as diagnostic aids. Vehicles are manufactured to comply with emission regulations, but this doesn't mean that all cars are subject to the same levels of control. The year the vehicle was constructed plays a major role in their allowable emission outputs. It would be inconceivable to expect a vehicle constructed in the 1970s to meet the current Euro 5 or 6 standards imposed on us today. So allowances must be made when interpreting the data from the gas analyser. To explain this, we'll look at two very different vehicles with the same faults induced. Our two test vehicles are both gasoline injected, but only the newer one has any control over exhaust emissions. We need to start with some idea of what correctly functioning vehicles should look like on the gas analyser. At idle, our two vehicles have these readings. We can see the GDI vehicle has a very low hydrocarbon count. CO, O2 and NOx are at 0, while lambda and air-fuel ratios are perfect. Whereas the 20-year-old indirect injected vehicle has somewhat higher readings. But if we compare the CO2 values, we can see they are sitting at around 15%. This is exactly what we want to see for a correctly operating engine. At 2500 RPMs, the values change a little. The GDI vehicle experiences a slight increase in hydrocarbons and carbon monoxide, with a predictable drop in carbon dioxide. Our MPI vehicle has similar results, except the NOx levels have increased. Again, this is due to the lack of an exhaust catalyst on this one. Okay, now that we have these base values to refer to, let's induce some faults and interpret the results. The multi-point injected vehicle with the misfire has had a dramatic change of exhaust tailpipe emissions. The hydrocarbon values have gone through the roof to 800 parts per million, with the CO2 content dropping to 7.5% and oxygen values sitting on around 10%. The increase in hydrocarbons indicates a rich mixture resembling an ignition fault. We can see the gasoline direct injected vehicle is experiencing similar increases in hydrocarbon and decreases in carbon dioxide, but to a much lesser degree. Both vehicles now have a blocked fuel injector. Let's have a look at the change in exhaust emissions. At idle on the older vehicle, the hydrocarbons have increased slightly, but at 2500 RPMs, there are less than half of what a correctly functioning system should be. This is due to the fuel trims being corrected by the ECM at idle. The engine management system has increased the pulse width on the other cylinders to compensate for the lean burn. At 2500 RPMs, the ECM is unable to correct with fuel trims alone, so we see the hydrocarbon content reducing. We can see the CO2 levels have dropped from ideal to roughly 12%. The newer vehicle has again shown similar readings to the old one. At idle, we see slightly higher hydrocarbon readings than normal, indicating an increased pulse width at the injectors, but it's the increase in oxygen content that confirms a problem. The high oxygen indicates air is being drawn into the cylinders, but with no additional fuel. Again, at both idle and 2500 RPMs, we can see a reduction in CO2 emissions, indicating an efficiency problem. Something to pay attention to here are the NOx levels. An increase in oxygen is preventing the catalyst from operating correctly. In this test, we have an intake manifold leak on both vehicles. Both vehicles have shown us similar results with increases in oxygen content and decreases in CO2 output. Air is drawn into the engine after the mass airflow sensor. This is also evident in the hydrocarbon levels decreasing. You will also notice the air-fuel ratios are at the lean end of the spectrum. This next set of results shows both vehicles with very high fuel delivery pressure. This proves that regardless of the system, the values will be similar. The biggest change we can see is at idle speed in the hydrocarbon count. Higher than desired fuel pressure will result in more fuel flow past the injectors. We can also see the CO concentration has increased dramatically. The air-fuel ratios also show an overall rich mixture. Okay, some facts to remember when using a gas analyzer are: CO2 is an indicator of combustion efficiency that peaks at or near the stoichiometric air-fuel ratios and decreases with lean or rich air-fuel ratios. An increase in NOx will result in a decrease of both hydrocarbons and carbon monoxide. Hydrocarbons are an indicator of the fuel mixture and will change if a lean or rich misfire occurs. Carbon monoxide is an indicator of combustion mixtures. An engine running lean or rich but not misfiring will be seen as an increase or decrease in CO values. Oxygen in high quantities will represent an air leak in the intake or exhaust system. Using a gas analyzer is a great way to localise faults to an engine main or subsystem. Interpreting them correctly will make diagnosis simple. Thanks for watching.